All right, so it says here, assume that x is x of t and y is y of t. All that's saying to you is this. Assume that the x value of this equation is a function of t, like we talked about t as being time. And assume that y is some function of time. Then find the indicated rate given the other information. So I'm going to start by doing number 10. So you're going to do 9 for homework. I'm going to do number 10 in class, all right? And I'm going to try and do this a little bit more now, where I'm going to just go to I'm going to introduce material, ideas, concepts. Then I'm going to go and I'm going to do homework problems very similar to the ones you're going to do, all right? All right, so we are given an equation. I'm going to write it down on the board, and then we're going to work it through. So we have y equals x cubed minus 3. We're given that dx dt is negative 2 when x is 2. And we're asked to find dy dt. Sorry, this is so messy with me writing that down, but I'll get it out of here. Okay, so there we go. So we're given this equation, right? We're given that equation. We're told that dx dt is negative 2 when x is equal to 2. And we're asked to find dy dt. So the thing we're trying to find here is the derivative of y with respect to t, right? That means we're going to take this equation and we're going to differentiate it with respect to t. And notice t does not appear here, right? So let's start seeing if we can get this straightened out, because I know we had problems with this last class. What is the derivative of y with respect to t? dy dt, right? Now, we had in the past called it y prime, but now we're calling it dy dt. All right? That's all right. So that's dy dt equals, now, this is the part that I think most people were having issues with. The derivative of x cubed. So what we normally had said was 3x squared, right, in the past? Right? But this is what's really happening, and I want to kind of show this to you a different way. Let's say that we have something here. I'm going to call it junk, right? Say we have some junk sitting in a trunk. All right? And it's raised to the nth power. Yes? All right. If we take the derivative of something like this, we use the power rule, which says that the n comes out. Then we have the junk, right? To what power? N minus 1. So what's happening here is the power rule says take the n out, subtract 1 from the n, but don't touch the junk, all right? Yes? Just leave it alone. And then after that, chain rule says multiply by the derivative of the junk. Now you're allowed to take the derivative. So you take the junk, you take its derivative, right? Okay. When in the past, when we've taken the derivative of x cubed, we've always said that's just 3x squared, right? But let's use this rule right here. What is our junk? What is the junk in this problem? The x, right? That's our junk. So according to this rule, we're going to have a 3, right? That's this. Then what? The x, which is the junk, to what power? Squared, which is what we're used to, yes? But then times the derivative of x, right? The derivative of x. Normally that would be 1. If we're differentiating with respect to x, the answer is 1. But what if we're differentiating with respect to t? Then the derivative of x is not 1, it's dx dt. Does that make sense? Like, if we're differentiating with respect to x, if this is x down here, then that would have been a 1. But if this is t down here, then that piece is going to be dx dt. Yes or no? Yes? Ask a question. Yeah.
Could you visualize the dt as like a z-axis, or does that not really work out like algebraically?
Yeah, you can't look at it like a z-axis now.
Yeah, okay. No z-axis.
Yeah, it's all a flat sheet of paper.
Okay.
Yeah.
Okay, so basically what you do is like converting the derivative of the jump to dx dt, correct?
Yeah, I think the confusion is when you took the derivative of this, I think most people are on board with this part. Okay, but it's this piece right here. Where is this coming from? It's coming from the chain rule. The chain rule says you always have to have the derivative of the junk here. This right here will always be determined by what we're differentiating with respect to. It's always determined by this right here. If that was x, okay, if I had asked for dy dx, then how would this problem have changed? The left side would have been what? It would have been dy dx, right? And then this would have been what? Derivative of this would be 3x squared times 1, right? This would have been 1. Because dx would have been 1. I still don't feel like it's going through, but we're going to have to push ahead. Let's see. Derivative of that with respect to t. So what is it? 3x squared times dx dt. And we are done taking the derivative of x cubed. Now we move on, minus the derivative of 3, and the derivative of 3 is still 0. Okay, so that's it. This is the result of taking the derivative. Now this is not our final answer, right? No, because we're asked to find dy dt when x is 2 and dx dt is negative 2. So all that means is we're just going to plug these in. Like this right here is like a variable, this is a variable, and we're going to replace them right here. So in this equation, we leave the 3. What's our x here? 2. That's given to us in the problem. We have to square that, right? And then multiply by whatever dx dt is, and that's given to us to be negative 2. So this is order of operations. We do this first, right? So 4, 12, negative 24.
Is writing dy dt the same thing as writing y parentheses t?
Y parentheses.
T and then close it?
You're asking, is this the same as writing y parentheses t?
Yeah.
It would be the same as writing y prime parentheses t.
Okay, that's good to know.
Yeah. That would be the same notation. All right, let's try another one of these. So the next example, where is it? Keep doing the wrong one there. Let's look at number 12. Bring it up there. All right, we have x squared plus y squared equals 4. They're giving us that dy dt is 5 when x is 1.2 and y is negative 1.6. And we're asked to find dx dt. What are we differentiating with respect to? We're differentiating with respect to t, all right? So that means that nothing is going to, the derivative, will never have a derivative be 1 unless t appears in here, which it doesn't. So let's start with this and let's take the derivative of this. So what is the derivative of x squared? 2x times dx dt. This is that chain rule happening. You had the junk squared, right? Derivative of the junk squared was 2 times the junk. But then you have to say times the derivative of the junk, right? And what's the derivative of x? Well, with respect to t, it's dx dt. Am I done with x squared? No?
Oh, with x, yes.
With the x squared. Am I done with the x squared? Yes. Okay, so now I can say plus because I have addition here. Now, this one right here is something that people got wrong on the test. The derivative of y squared with respect to t. What is it? 2y times dy dt.
Oh, it's not, oh, no.
Yeah, get the whole prime. Let's get the primes out of here. Yeah, because the primes are not good for this sort of problem because they don't keep track of what variables here. So that is the chain rule, right? We had something, right? Some junk here squared. So we brought the 2 down, rewrote the junk to the first power, and then we took the derivative of the y itself, which in this case is dy dt. We clear with that? Okay, moving on. Equals 0. All right, now, what are we trying to find here? We're asked to find dx dt, right? We're asked to find this, which means we're trying to find that, right? And it appears there it is. Now, the only way we can find that, the only way I can tell you what dx dt is if I know what x is, if I know what y is, and if I know what dy dt is. If I know what all 3 of these things are, then I can tell you what that is, right? Do I know them? Yeah, they're given to me, right? X is 1.2, y is negative 1.6, and dy dt is 5. So now I replace everything. 2, 1.2, dx dt, plus 2 times y, which is negative 1.6, times dy dt, which is 5. That must equal 0. So notice by replacing all my variables with the numbers, I only have one expression, one variable expression left, and that's dx dt, right? And that's what I'm looking for. So now we just do some multiplication. Since these are decimals, if you need your calculator, get your calculator out, whatever. These two together, 2.4 dx dt. And then plus, when you multiply these, you go this times this, and then that times 5. So
It's negative 3.2. It's going to be a negative 16.
negative 16 total.
Yeah.
And then equals 0. Now I'm trying to solve for this, right? So how am I going to get this? How do I solve for this at this point? Yeah, so try and isolate this. So let's move the 16 over first. So 2.4 dx dt is positive 16, moving the negative 16 to the other side. And then finally, divide by 2.4. So dx dt is 16 divided by 2.4.
Can we just simplify that though?
Pardon?
Can we just simplify 16?
It's 6.666? Oh, 6.666. Is that okay if I write that on the board? Anyone going to freak out? You can, yeah, you can reduce that or write a fraction if you want. What was your question? Yeah.
So I think, sir, actually, when I deposited my check last week, my savings, it actually got the number 666. So I just started freaking the hell out. You should take it down and give it to me. Very good. It was like 6.
Yeah, if you don't want it, you can just bring us that check.
You know what?
All right, let's do one more of these because this next one has something in it that, again, I think caused a little bit of trouble in the exam. All right, so I'm doing number 14. We have x squared minus 2xy minus y squared equals 7. I'm given that dy dt is negative 1 when x is 2 and y is negative 1. We want to find dx dt. Now I realize you sitting there like, this is a very mechanical process, and I really have not done a great job explaining why it is that we would ever want to do implicit differentiation. I get that. We're about to do some word problems. I hope that they will help shed some light on why we would want to do this, all right? So let's just make sure we got the mechanical part of this down first. We are going to look for dx dt, right? So we're differentiating with respect to t. Since there aren't any t's up there, we know we're never going to get 1, right? It's always going to be d something dt, d something dt. So we start with the x squared. We've been down this road already, haven't we? Derivative of x squared is 2x times dx dt. t. So that we've done already, right?
Yes, sir.
Now the next piece is the part that I believe is going to cause a little bit of an issue.
Product rule?
We have product rule. Good. So do y'all see we have x times y?
Yes, sir.
Because we have x times y, we have a product rule. So I want you to see that. Right here we have a product, right? Now what about the -2 out there, out in front? When we take derivatives, the constants out front just come along for the ride, right? So watch the way I'm going to write this. I'm going to put -2. Then I'm going to put a set of parentheses right here, because that -2 is going to multiply times whatever I get when I take the derivative of this, right? And remember with the product rule says you have to take derivative of the first one times the second one plus the derivative of the second one times the first one, right? That's kind of hopefully you're waking up in the middle of the night saying that to yourself, right? No? You're not there yet? No? All right, so I'm focusing just on that piece right there, right? So let's start out. What's the first part going to be? dx dt. Why not 1?
Because we're
Yeah, so you're taking derivative of x, right? With respect to t. So the derivative of x with respect to t is dx dt. All right, times what or plus what or what? Times y. So that's the first part of the product rule. You do derivative of this, which we did, dx dt, times this, y. Now what's the next part of the product rule? Plus. Now we take derivative of this, which is dy dt, times x. I have a question. Can I call you out? I'm going to call you out. All right. So you're kind of having some trouble in the beginning of the semester with this a little bit. Now you seem to get it. So are you something you're drinking? Are you taking a pill? Is there something that you're doing?
just a lot of tutoring.
Yeah, so you're getting help and you're working on it, right? I can tell. I mean, I've told you this already. I mean, you have to practice with this, right? If you don't get it, like if you get it, great, I'm happy for you, right? But if it's not automatic, you know, if you're not at that point yet, you just have to practice, get help. And then once, it's like a light bulb, right? Like once you get it, it's there, right? There's your product rule. Anyone have questions on where any of that came from? Okay, what do I do next?
You find the y.
Yeah, so we've got to do this piece, right? So minus, I'm just going to put the minus here. 2y dy dt. And then equals 0. That's it. Now we're trying to find dx dt, right? We're trying to find that. And it appears more than once, doesn't it? It appears here, and it appears here, right?
Can we take it out?
You could try and get the dx dt out by itself. You could, but because this problem gives you all the other information, we're just going to plug them in, and it'll get rid of all the variables, and we'll just have numbers in there. It'll be a lot easier to work with. So I'm going to rewrite this to, what am I going to replace x with? 2, because it told me, right? X is 2. Then we have dx dt minus 2 parentheses dx dt. We're not doing anything with that, right? Times y. What was y? -1. So -1 here. And that's being multiplied, right? Times this. Plus dy dt. -1 again, right? Times x,
Which is just
2. That's all in my parentheses, right? That was all sitting in here. So we're plugging and chugging. That's a common thing in math that teachers will be, oh, we're doing plug and chug now. We're just taking numbers, plugging them in, chugging out the answer. Keep going. Minus 2 times y, -1, times dy dt, which was -1 again, right? Equals 0. All right, now this right here, this looks pretty bad, but you know, this is just arithmetic. Let's take our time with it. 2 times 2 is 4, so 4 dx dt minus 2, let's see, parentheses here. What does this become? Can't really put them together, but I could write negative dx dt, right?
Wasn't he putting together though?
That is, yes. That's just, I don't want to write it like that anymore, so I'm just going to put the negative out in front of it.
Got it.
Now, how about this? Just minus 2. That's all still in parentheses. And then over here? So this together is plus 1, right? But then you're going to multiply that times this, so minus 2 again equals 0. Bless you. I'm trying to get dx dt by itself here, right? I'm trying to get dx dt. It's trapped. You see how it's trapped inside of here? How can I get this dx dt out of this thing? How do I get that dx dt out of that parentheses? Yeah, you've got to pass the negative 2 through. We need to distribute that negative 2 through the parentheses. So let's do that. 4 dx dt. What?
Plus.
Yeah, so minus and minus become plus, so we have plus 2 dx dt. And then we do minus and minus again, we get plus again, so plus what?
Plus 4.
4, and then we have back here minus 2. And now we have no more parentheses, so we can start putting things together. And this is kind of an interesting looking expression, but let's just think about it. It's like you've got 4 apples plus 2 apples, right? That's 6 apples. So you got 6 of these, don't you?
Yes, sir.
And then plus, we can put those together. It's 2. So we've got 6 dx dt's
Minus 2.
plus 2 equals 0, right?
Yes.
And now what?
We have to move the 2 over.
Move the 2 over and then divide by 6. Good. Nope. Move the 2 over, made it negative 2. And then divide both sides by 6. So dx dt equals, what is it? Negative 1/3. Questions? Is that, you think that's enough examples where you feel a little more comfortable with it?
Yeah.
Okay. Let's do some word problems so you can be confused then. If you're getting it, let's try and confuse you now. So I'd like for us to read through this first problem. Let me erase all this stuff. Now, number 33 is the problem that you'll be doing for homework. But I'm going to do number 34, which is down below this. But to do number 34, they're saying for 34, God, I keep doing that. They want us to repeat problem 33 for just some different functions. So we have to first read number 33. So we're talking about cost, revenue, and profit. Suppose that for a company manufacturing calculators, the cost, revenue, and profit equations are given. So here's our cost, revenue, and profit. And remember, profit is revenue minus cost. This next part of the given sentence is important. Where the production output in 1 week is X calculators. So the variable X that you see in these equations represents how many calculators are produced in 1 week for this company. All right? What we've introduced into the problem is something that we did not have in Math 1324. We never were talking about time when we were talking about cost and revenue. It was always just, here's your cost function, here's your revenue function, but the time aspect was not there. Like, we're making so many calculators per week, all right? If production is increasing at a rate of 500 calculators per week, when production output is 6,000 calculators, find the rate of increase or decrease of cost, revenue, and profit. You know what? Let's just do this one for your homework. Why don't you all do 34? We'll do it that way. That way I can keep everything on the board here. All right, let's read that again. I think it's worth reading. If production is increasing, so production is how many calculators we're making, right? If we are going to increase that rate by 500 calculators per week. So we're like, turn up the machines, crack the whips on the employees, whatever it takes. We need more calculators per week. We're going to increase it by 500 calculators per week. And we're doing that when production is already 6,000 calculators. So it's like my employees are making 6,000 calculators a week right now. And I'm going to go in there and we are increasing the production by 500 calculators a week, right? Come on, everyone, let's go. No raises. I'm going to take your lunch break away. We need more calculators per week, all right? We want to find the rate. And that word right there means derivative, okay? For us, when we see rate, we need to think derivative. We need to be looking for the rate of increase or decrease in cost, revenue, and profit. So the way we want to visualize this, or not visualize it, think about it, is that, we've got the company, we're making 6,000 calculators per week right now. If we increase the production level by 500 calculators a week, how is that going to impact is it going to impact my cost? Are we going to have an increase in cost? Or a decrease in cost? Are we going to have an increase in revenue or a decrease in revenue? Are we going to have an increase in profit or a decrease in profit? Does that make sense? Yes.
So are we using the equations for finding marginal profit, not exact?
This is not marginal profit. This is not marginal profit. Okay, this is something different. That's why it's important for us to understand the time aspect of this. All right. Find the rate at which this increases, these three things increase. All right, let's start with part A. All right, let's start with part A. And I think what I'll do, I think I can make this smaller. Bring it over here. Yeah. Okay, so I'm going to start with the cost. Can you all see that okay? Bring my cost up. Let's start with the cost. Part A. Okay, what am I trying to find? That's the first thing. What am I trying to find for part A? Okay, not cost. Find the rate of the increase or decrease in cost. So that means you're trying to find the derivative of cost. The derivative of cost with respect to what? With x, that's one possibility. It could be dc dx, right? Or it could be dc dt, right? Because rate, it's a rate. The rate tells us derivative, but it's which one? We're trying to find the rate of increase and decrease in cost if we are changing our rate of production per week. When you see here week, is that a measurement of time or is that a measurement of how many calculators are made? Time, right? A week is a measurement of time. So this first part is asking us for dc dt. That's what we want. Now, let's go up and take, you know what? Should we talk about what's given to us here? In the previous problems, I said, here's an equation, right? Then I said, we're given this, and we're asked to find something, right? And we took the derivative and then we plugged things in. Okay, this is the same type of problem. This is what we want to find, right? Do we have an equation for cost? Yes, it's up there. Now, is there anything that we're given in the problem? Do we know anything? What does this 500 represent?
The amount calculated.
It's the, okay, so if production is increasing at a rate, what's production again? Production is the output, X calculators, right? Production is how many calculators we're making, which is X. If our rate of production is increasing at a rate of 500 calculators per week, then dx dt must be 500. Do you all see how that 500 is dx dt? It's the rate at which your production is changing. Right? Production is increasing. What is production? Production is x. So it's the rate at which x is changing with respect to time. Follow me or not? Okay. What's the 6,000 then? That is what x is right now, right? That's our current production level is 6,000, isn't it? That's what that's saying. Notice that with 6,000, It's not talking about a rate, right? It says when production output is 6,000. It doesn't say when the rate of production or anything like that. It's talking about just the production itself. So this is giving me that X is 6,000. So I want to find this when these two are given to be this. What's my next step?
Start plugging it in.
Plug it in? Yeah, I'm going to plug these in, but plug them into what? I have to take its derivative first, don't I?
30.
Yep. So let's take our cost function. 90,000 plus 30x. And let's take the derivative of this with respect to t. So what's the left side? dc dt. The derivative of 90,000 is 0, right? Plus 30 times the derivative of x, which is 1. No, it's dx dt. That's right, okay? It's dx dt. Right? So what was it we were trying to find? dc dt, right? Here's what we're given, right? Can we get dc dt? Yeah, we just need that. And we have that, don't we?
Yes.
Now we also have this 6,000. And that didn't come into play here, did it? It will when we get to the revenue function, though. When we get to the revenue function, we're actually going to have some x's in there when we take the derivative, and it will matter. So it looks like our cost is, if you look at it this way, our change in cost, the rate at which our cost is changing with respect to time, is only a function of how we change our production. If we change our production, our costs go up. But what our production level is at that point doesn't matter. So what would dc dt be?
15,000.
So you're just going to replace that with 500, right? So 15,000?
Over 1 week.
Yeah, so now the next part is very important, all right? And on your test, I did take off for you not explaining what your answer meant. Like you may have gotten the right numerical answer, but you didn't explain what it was. So we all understand where 15,000 comes from, right? That's this being replaced with 500, right?
Yes.
Okay, and multiplying. Okay. Now, to figure out what this is, the easiest way I think I can explain it to you, and this is the way I explain it to my regular Cal 1 students, is that all you have to do is look at the two variables here and talk about what they are measuring. So what is cost measuring here? Cost is money, right? Dollars, yes? So this is $15,000, okay? Now, division means per, right? When you're sitting there driving down the road, miles per hour means miles over hours. So when we're saying cost over time, this is cost is measured in dollars, and then what's time measured in this particular problem? Weeks. So this is per week. My company's making 6,000 calculators a week. If I bump that up by 500 calculators per week, the costs for my company are going to go up by $15,000 per week. Yes?
Sir, I did not know division means per. I did not know division means per.
Okay. Good. You learned something today. There you go. So right now, as the CEO, owner of this company, I'm not quite sure I want to increase production levels because it's going to increase my cost, isn't it? By quite a bit, 15,000. But that's not all I would look at, right? That's not the only thing I would look at as a company. I would also want to look at how this is going to impact my revenue, right? So I know I'm going to have more money going out, but let's see how much more money I'm going to have coming in. So now to do part B, don't I still have the same given information? I still have dx dt is, well, what do I want? Sorry, what do I want? I want dr dt. Right? I'm going to put that equals question mark. That's because I'm asked for it, right? What's the increase or decrease in revenue? All right, dx dt is given to me in the problem to be 500 because, well, that's that sentence that we read. And then x by production level, my current production level is 6,000. So what do? We want to find dr dt. And we have that information. Take the revenue equation, right? Differentiate it with respect to x. Take that back with respect to t. So take my revenue equation, 300x, and then look at that next part, minus x squared over 30. I'm going to write that like this, minus 1/30 times x squared. That's the same expression. Taking something and dividing it by 30 is the same as multiplying it by 1/30. And the reason I like that is because it allows me to just ignore the constant and do my little chain rule right here. That's my revenue function. Ready for the derivative? Okay, what's the derivative of r? dr dt, right? dr dt. Why is it dr dt? Because we're differentiating with respect to time, right? Okay, what is the derivative? Be very careful. What's the derivative of 300x? 300 times dx dt. Now, negative 30 is going to come for the ride, right? Because it's attached to the front. Negative 1/30. Did I say negative 30? Yeah. Negative 1/30 comes for the ride. And now I'm trying to take derivative of x squared. Junk squared, right? Is what? 2x times dx dt. I think y'all are catching on to this. At least I feel better about this than I did the last time we talked about it. What's that?
Oh, I said same.
Yeah, you feel the same? Okay, good.
I watched that video and you're just like, I'm so nervous. Like you just kept saying, I'm so nervous for you guys.
Yeah, I felt like that. I feel a little better today, though. All right, we're trying to solve for dr dt, right?
Right.
There it is. In order to do that, we need to know what dx dt is, which we have, and we need to know what x is. See how x does come into play here? All right, so now it's just plug and chug. Plug everything in. Let's see what we get. So I'm replacing dx dt with 500 and x with 6,000. Any questions? dr dt equals 300 times 500 minus, let's see, that right there is really 1/15 if I reduce the fraction. And then x, what's x? Don't forget this x. This x is very important. What is this? It's 6,000, okay? That 6,000 comes into play in this problem because we have an x here, right? Where in the previous one we didn't. And then we also have dx dt, which is another 500. And now we get to kind of multiply this all out. I have a bad feeling about this for our company. I think we're getting negative change in revenue. I don't know.
I'm not charged. You were charged, sir.
Yes, you're right. Let's see what it turns out to be. dr dt is this right here. It's 150,000, right?
Oh my.
Right? That's different from the last problem. Wasn't it 30 times 500? This is 300 times. So it's 150,000 minus, now someone go ahead and help me get this here. This is 400?
Yeah.
400. So is this
3 million?
what, 3 million? Hold on. Did you divide by 15? Divide by 15?
Divided by 50. 0.06.
He was joking. He's joking. No. Oh, made a mistake.
What do you got? No?
Oh, what did you get for 60,000? Minus 115.
That's right.
Oh, but I didn't divide it by 19. I just did 6.
What is it divided by 15?
Is it 400?
400? Yes, I know this is 400 times 500, right? So 200,000. Okay.
What are we going on here?
All right, I want to make sure y'all are getting it though. 200,000 there? And then subtract, and you get negative 50,000. Negative 50,000.
That's a lot, okay.
Right? Negative 50,000 what?
That's revenue we.
Okay, it's revenue per time, right? What's revenue measured in? Money, right? Money is measured in dollars, right? So this is negative $50,000 per, what's our time measurement in the problem? Week. Okay, I'm not quite sure we should be increasing our production level, right? Because what happened? I mean, when we brought up when we were making 6,000 calculators per week, we said, hey, let's up it by 500, right? When we did that, our costs went up, right? That's part A, and our revenue went down. That's not good, right? Okay. So what's the answer to part C?
Just plug in the two answers you got.
So part C, check this out. Profit is revenue, right, minus cost. Yes? That's what this is, right? Now see if you can follow this. This is a little bit, a little weird. What am I looking for in part C?
Profit.
Not profit. The rate that profit's changing with respect to time, right? So like this one we wanted dc dt, right? Here dr dt. Here we want dp dt, right? That's what we want? Okay, so let me write that down. We want dp dt equals this. Right? That's what we want. But I don't have a profit function exactly, right, of x. All I have is this. And that's from 1324. We know profit is revenue minus cost, right? So how am I going to get dp dt from this equation? Well, just take the derivative of it. Take the derivative with respect to time. What is the derivative of p with respect to t? dp dt, right? So I'm about to differentiate this. This right here, when I differentiate it with respect to time, is dp dt equals, all right, what's the derivative of r with respect to t? dr dt. Okay, minus, what's the derivative of c with respect to t? dc dt. And guess what? dr dt is part B, and dc dt is part A, isn't it? We know what these are because we did parts A and B of the problem. So this is equal to, what was our answer for dr dt? That was this one? No, dr dt. This was this one, right? Negative 50,000, right? And then we're going to subtract from that, what was dc dt? 15,000. And so at the end of the day, this is negative 65,000, isn't it? Negative 65,000 what? P is profit in dollars per week. So you fire this guy who's running your production level at this point, right? Because there's no reason for us to increase production level. In fact, we might want to decrease it. Because maybe if we decrease it, maybe our costs go down and our revenue goes up. And therefore maybe our profit goes up, right? It's possible that you're making too many calculators and you're not selling them fast enough or something, right? Does this make sense? Can you see now how we can connect implicit differentiation to like kind of a real world situation a little bit? Okay. So for your homework, we're not done, okay? But for your homework, I want you to do number 34. So follow your list of problems that's on your schedule, but instead of doing problem 33, do 34. And basically what they tell you is you have like the same situation. They give you a cost function, they give you a revenue function, they tell you profit is revenue minus cost. So it's the exact same setup, except well, and they also tell you your production level is increasing at 500 calculators per week. So that's the same, isn't it? Yes? But your current production level is 1,500, not 6,000. Okay, so things are going to change. You're going to get different results here. What if this said where production is decreasing at a rate of 500? What if it said that? You would use a negative 500. Y'all catch that? If that said decreasing, right there, then dx dt would be negative 500, not positive 500. All right. I feel kind of good about this now.
So we're on 12.2.
Yeah, can I see that real quick? We are, in our homework, we are in 11.6. Yeah, so we are behind a little bit. So the 11.6 was not on the test. Like, I didn't ask you these word problems. So you want to do these homework assignments now. Yeah? Okay, we still have another word problem in this section. If I can find it. Where is it? I think this is it. Yeah. So I'm going to tell y'all a story here, all right? I'll make it quick. I'll try and make it quick. I'm only telling you this story because for some reason it kind of helps students, I don't know, they just seem to remember this whole idea of how important it is to know what you're differentiating with respect to, like whether or not it's with respect to time or with respect to X or whatever it is, right? So when I was in grad school, I'm actually going to mute my microphone because this is probably don't know why I don't like that on camera, but I mean, I don't like to talk about it. I was of age, by the way. I was of age. Huh? What's that? I didn't mention her name. I didn't mention her name. Her name's Shady, actually. Shady. I think it's Shadi or something like that, but I called her Shady, so. She was shady, yes. Okay. So look, if you have any equation out here, right? So look at this equation. It's a price-demand equation. There it is. I can differentiate that with respect to anything I want. I can differentiate that with respect to X, with respect to P, with respect to T, right? I could differentiate that thing with respect to R, even though there's not an R up there. But then you'd have to say, what does it mean? What does dx dr mean? Well, for us, time is now the critical element in these problems. We want to be able to talk about how fast something is changing with respect to time. So how about I'll do 37, you do 38? You want to do that again? This will be our last problem. We have about 12 minutes. Okay. The price, P in dollars, and demand, X for a product are related by this. So P is price. Can you all read that? Do I need to make that bigger?
37.
Yeah, we're doing 37. Okay, so P is price, right, in dollars. And demand is X. So X is the number of items that are demanded, whether it be calculators or whatever it is. Did I even mention that here? No, they don't, right? Do you see time anywhere in here? Are they talking about time here? No, talking about dollars and demand. The money, right? And how many products we have. Now, look at the question, part A. If the price is increasing at a rate means derivative, right? So if the price is increasing at a rate of $2 per month, now we've got time in the problem, right? When the price is $30, find the rate, derivative, right, of change in demand. And what is demand in our problem? X. Okay, so let's see if we can't take all of that word problem that we just read and turn it into some mathy stuff. Hold on, I will answer that as soon as I get this up here. So who said what? That's right. They want us to find dx dt. They want us to find the rate, which is a derivative. The derivative of what? Demand. What is demand? X. They want dx with respect to time. So we want dx dt. Okay, now do we have any given information that's going to help us get dx dt? There's more stuff in the problem, right? There's more stuff in here. Price is increasing at a rate. So isn't price rate, isn't that the derivative of price?
Yes.
Okay, and it's $2 per month, and that's a measurement of time. dp dt, capital P, lowercase p. dp dt is what?
2.
2. Now it's positive 2 because it's increasing. Had that been decreasing, we would have put negative 2. Make sense? Price increasing at a rate of $2 per month. Now it also says when the price is 30.
That's P.
That's just P. See, because when it says price is 30, it's not saying rate of price, right? It's just saying price. So this means P is 30. So we're supposed to find dx dt when the price is changing at $2 per month and when the price has been set at $30. You ready to do this? You ready? Okay, so what do we need to do now? We need to take the derivative of that, everyone. That's going to be sucky, but all right, let me write that down. 2x squared plus 5xp plus 50p squared equals 80,000. Yeah, I think Shady's when she got married, I think her husband, it was a cultural thing. She wasn't really allowed to talk to me anymore. You know, some cultures are like that, you know. It's like, and even, you don't even have to be cultural. There's some men that can't stand their wives having friends. So, you know how that can be, yeah? My wife and I are cool like that. Like, we totally get it, so. All right, you ready? This derivative is going to be a little messy. All right, let's take our time through it. What's the derivative of 2x squared?
4x.
So 2 drops out, 4x times dx dt. So there's that chain rule happening, right? The 2's coming out, we're leaving x to the first power, derivative of x, dx dt. Plus, that's product rule, right? So I'm going to put the 5 here, and then I'm going to put a parentheses, because I'm about to do the product rule right between these two, right? Yeah, what is it?
dx dt times p, then dp
Dx dt times p, then plus
dp times
dp dt times x. Close the parentheses.
tongue twister, okay?
Yeah, it is, isn't it?
And the next one would be the 100p times dp over 2.
Exactly. So we got 50p squared. We bring the 2 down. That makes that 100. P to the first power. But then times dp dt
Equals 0.
equals 0.
And that's when you multiply the 5, right?
We'll distribute. But I'm not even going to do that yet. I just want to take a step back and look at what we have, okay? Because we're close to having an answer. But this problem is actually presenting us with an issue we have not seen yet. We are wanting to find dx dt, right? And it appears here and here. Anywhere else? That's it, right? Those are the only places. Now, I'm going to be able to come into the problem